In this video, we are going to see some examples of topologies on real line. The first example of topology is discrete topology on real line. Discrete topology. So as in the previous video, discrete topology is denoted by TOD. It consists of all subsets of real line. All subsets of real line. And this is the largest topology also. And another topology on real line is indiscrete topology, which is the smallest topology in discrete topology. It is actually denoted by tau I, and which consists of only two sets of the form empty set and the full set. Here the full set is real line. And another topology is standard topology, or it is called usual topology. Usual topology on real line. And actually it is denoted by tau u. And what is tau u? It is collection of all some subsets of real line such that it has the property that for a very small a in capital A, there exists some r greater than 0, positive real number greater than 0, such that interval of the form a minus r, a plus r is fully contained in A itself. When it satisfies this property, that kind of subsets belongs to this collection tau u. And I can prove that this tau u is a topology. Okay, we will see the proof. Tau u is a topology. First of all, empty set is clearly belongs to tau u because it has no elements. It trivially satisfies this property. And the full set this is the first axiom of topology, and second axiom is full set should be belongs to tau u. What is the full set here? It is real line itself. So we have to say R belongs to tau u. Okay, for that real line has the required property. So I take let A is a member in the full set R. Then we want a real number r greater than 0 such that this interval is fully contained in real line itself. For that I take r equal to 1. Then you consider the interval a minus r, a plus r. What is this interval a minus r, a plus r? A minus 1, a plus 1. When a is a real number and 1 is a real number, a minus 1 and a plus 1 is a real number. So in between these two real numbers, every number is a real number. So all these numbers are clearly belongs to real line itself, right? Because suppose this is our real line, a is a number here, a minus 1 will belongs to the left of a and a plus 1 belongs to the right of a, correct? So this interval, that means any elements between these two, a minus 1 and a plus 1. Clearly all these numbers from these lines are belongs to real line itself. Therefore, this interval is actually contained in real line itself, which implies the full set has the required property. Therefore, full set belongs to tau u. Now, we have to verify two more axioms. Now, the third axiom is tau u is closed under. We have to prove tau u is closed under arbitrary union. For that, I consider some collection of sets from tau u. Suppose collection of A alphas are members in tau u, which implies actually every A alpha is a member in tau u. Okay. Now, we have to prove union alpha A alpha belongs to tau u. So, union alpha A alpha should contain that property. For that, let A is a member. ഏത് സെറ്റാണോ നമുക്ക് ടോ യുവിലെ മെമ്പറാണെന്ന് പ്രൂവ് ചെയ്യേണ്ടത്, ആ സെറ്റിൽ ഒരു എലമെൻ്റ് എടുക്കുന്നു, ആ എലമെൻറ്റിന് കറസ്പോണ്ടിങ് ആയിട്ട് ഒരു ഇൻട്രവൽ മുഴുവനായിട്ടും ടോ യു സെറ്റിലുണ്ട് എന്ന് പ്രൂവ് ചെയ്യുന്നു. അപ്പോഴാണ് ആ സെറ്റ് നമുക്ക് ടോ യുവിലെ മെമ്പറാണെന്ന് പറയാൻ പറ്റുക. ഫോർ ദാറ്റ് ലെറ്റ് എ ഈസ് എ മെമ്പർ ഇൻ യൂണിയൻ ആൽഫ എ ആൽഫ, ബിക്കോസ് വി ഹാവ് ടു പ്രൂവ് യൂണിയൻ ആൽഫ എ ആൽഫ ബിലോങ്സ് ടു ടോ യു. അപ്പോൾ ഏതാണോ ടോ യുവിലെ മെമ്പറാണെന്ന് കാണിക്കേണ്ടത് ആ സെറ്റിലാണ് നമ്മൾ എലമെൻ്റ് എടുക്കുന്നത്. ഇനി ഈ എലമെൻറ്റിന് കറസ്പോണ്ടിങ് ആയിട്ട് നമുക്കൊരു റിയൽ നമ്പർ ആർ കണ്ടുപിടിക്കാൻ പറ്റണം, സച്ച് എ വേ ദാറ്റ് ഇൻട്രവൽ എ മൈനസ് ആർ, എ പ്ലസ് ആർ ഇസ് കണ്ടെയ്ൻഡ് ഇൻ യൂണിയൻ ആൽഫ എ ആൽഫ ഇറ്റ് സെൽഫ്. ഓക്കെ, വെൻ എ ബിലോങ്സ് ടു യൂണിയൻ ആൽഫ എ ആൽഫ, വാട്ട് യു ക്യാൻ സേ എ ബിലോങ്സ് ടു സം എ ആൽഫ നോട്ട് ഫോർ സം ആൽഫ നോട്ട്. യൂണിയനിലുണ്ടെങ്കിൽ ഏതെങ്കിലും ഒരു ആൽഫയിലുണ്ടെന്ന് പറയാൻ പറ്റുക. സോ ദാറ്റ് ആൽഫ നോട്ട് ഈസ് ഐ ടേക്കൺ ആസ് എ ആൽഫ നോട്ട്. So A belongs to A alpha naught. And what do you know? A alpha naught is a member of tau u. Correct? Because collection A alpha tau u lana, appo A alpha naught tau u lana. So A alpha naught tau u implies there exists some R naught greater than 0 such that we can write the interval A minus alpha R naught, A plus R naught will be fully contained in A alpha naught. Okay, and what is this A alpha naught? A alpha naught is a member from this collection. So A alpha, where is this A alpha naught contained in? A alpha naught clearly will be contained in union alpha A alpha, because A alpha naught is a one member from this union. So which implies this interval itself will be contained in this union. Which implies when you take an element from this union, we get some radius, we get some real number R naught, such that this kind of interval is completely contained in that set. Therefore, this set has the required property of tau u, which implies union alpha A alpha belongs to tau u. So tau u is closed under arbitrary union. It's true. For the last property of the topology, tau u is closed under finite intersection. So, tau u closed under finite intersection means when you consider some finite number of elements from tau u, their intersection is also belongs to tau u. That is our A. So, let some A1, A2, etc. This is some enumeration. An belongs to tau u. I take finite number of elements from tau u. We need to prove that intersection I equal to 1 to n Ai also belongs to tau u. This is our A. Aim is to prove that intersection I equal to 1 to n Ai belongs to tau u. So what you want to prove? We take an arbitrary element from this set. This is a set. And we want some interval of the form A minus R, A plus R belongs to this intersection itself. Okay? Okay, I take let A is a member in the set which should be in tau u. Intersection I equal to 1 to n to Ai. When A belongs to some intersection implies A belongs to Ai for every I equal to 1, 2, 3, etc. n by the definition of intersection. And what you know about this Ai's? Each Ai, since each Ai belongs to tau u corresponding to every I, ഓരോ എയും A1 ഉണ്ടെങ്കിൽ കറസ്പോണ്ടിങ് ആയിട്ടൊരു റേഡിയസ് R1 ഉണ്ടാവും, സച്ച് ദാറ്റ് A minus R1, A plus R1 belongs to. നോക്കൂ, if A belongs to A1, what you can say about A1 is a member in tau u, there exists some R1 greater than 0 such that interval of the form A minus R1, A plus R1 will be contained in A1. Similarly, since A belongs to A2, there exists some radius R2. So as in generally what you can write? Generally, A belongs to Ai implies there exists some Ri greater than 0 such that interval of the form A minus Ri, A plus Ri is completely contained in Ai, the corresponding I for every I equal to 1, 2, 3, etc. n. Okay, now we have now R1, R2, R3, etc. Rn, n number of positive real numbers. Using these positive real numbers, I choose a real number R. Let R equal to minimum of R1, R2, etc. Rn. Okay, then what can you say about this real number R? R is again positive because all these Ri's are positive. Okay, then you consider the interval of the form A minus R, A plus R. You can see that this is the smallest interval among all these A minus Ri, A plus Ri, because R is the smallest radius. So which will be contained in A minus Ri, comma A plus Ri for every I equal to 1, 2, 3, etc. n. Okay, which implies interval A minus R, A plus R will be contained in since it belongs to all of these intervals, it should be belongs to their intersection. Intersection I equal to 1 to n, a minus ri, a plus ri. And where this interval a minus ri, a plus ri is contained, which is actually contained in corresponding AIs, the set AIs. So this will be contained in intersection I equal to 1 to n capital AI. So when you take an element small a from this intersection, we get now real number r such that a minus r, a plus r is contained in that intersection set. So this intersection set has the required property of tau u. Therefore, intersection I equal to 1 to n ai is a member in tau u. So tau u has all the properties of topology. Therefore, tau u is a topology on real line, and this topology is called usual topology or standard topology of real line. Now one more topology, that is semi-open interval topology on real line. So before defining the semi-open interval topology, do you remember sets in real line of the form half open intervals? So using this kind of intervals, we are going to define some topology that is actually called the semi-open interval topology. Okay, so for that I can define actually these two kinds of subsets in real line, right? So we can define two kind of semi-open interval topology on real line. I choose to denote tau ls. This topology actually also called lower limit topologies. I define tau ls, this is just a representation, tau ls, which is equal to collection of A subsets of real line such that for every A in A, there exists some r greater than 0, real number r greater than 0, such that interval of the form A comma A plus r is contained in A itself. This is something very much similar to the previous one, the usual topology. There the interval of the form A minus r, A plus r. A is here, A minus r will be here, and A plus r will be here. In usual topology, we need these kinds of intervals. Here tau ls, we need only this kind of interval, this one. Okay. This is our tau ls, and I define tau rs. Tau rs is equal to the reverse one, the next portion of the interval. Set of all A subset of R such that for every A in A, comma, there exists R greater than 0 such that interval of the form A minus R A. This interval, this belongs to tau rs and this belongs to tau ls, is completely contained in A. These are the two kind of semi-open interval topologies. Okay. This is actually this tau ls is representation of left closed and tau rs is right closed format. Here it is left closed format. That's why I chose L and R. Left closed semi-open interval topology, right closed semi-open interval topology. Okay. These two are the semi-open interval topologies. Okay, we will prove this is a topology. So claim tau ls, similarly tau rs is a topology. So I will prove tau ls is a topology on our real line. Okay, so we have to verify again the 4 axioms. It is easy because the proof is much similar as usual topology. The first property, empty set. Obviously empty set belongs to tau ls because it has no elements. Second one, real line itself is contained in tau ls. Why? Because when you take an real line and A is an element in real line, then for any real number, A closed open A plus R surely is contained in real number, because any number between A and A plus R is a real number, right? So the all of them belongs to real line itself. Therefore this interval completely is contained in real line itself. അല്ലേ, നമ്മൾ ഏത് റേഡിയസ് എടുത്തു കഴിഞ്ഞാലും ഒരു എലമെൻറ്റ് പെർട്ടിക്കുലർ എലമെൻറ്റ് നമ്മൾ ഫിക്സ് ചെയ്ത് കഴിഞ്ഞാൽ ഏത് റേഡിയസ് എടുത്തു കഴിഞ്ഞാലും ഈ ഇൻ്റർവെല്ലിൽ വരുള്ളൂ. this interval എവിടെ കിടക്കുന്ന റിയൽ ലൈൻ്റെ ഉള്ളിൽ തന്നെ ഉള്ളത് അല്ലേ. സോ ദിസ് ഈസ് കംപ്ലീറ്റ്ലി കണ്ടെയ്ൻഡ് ഇൻ റിയൽ ലൈൻ ഇറ്റ് സെൽഫ്. therefore റിയൽ ലൈൻ belongs to tau ls. Now we need only prove that tau ls is closed under arbitrary union. For that, collection A alphas are members from tau ls. Okay, we want union A alpha belongs to tau ls. How will you prove that union A alpha belongs to tau ls? ദാ നോക്കൂ, tau ls-ൽ ഒരു സെറ്റ് വരണമെങ്കിൽ tau ls-ൽ ഒരു സെറ്റ് ഇൻക്ലൂഡ് ചെയ്യണമെങ്കിൽ ആ സെറ്റിലെ ഏത് എലമെൻ്റ് എടുത്താലും ഈ ടൈപ്പ് ഓഫ് ഇൻ്റർവൽ ആ സെറ്റിനകത്തുണ്ടെന്ന് കാണിക്കണം. സോ വി നീഡ് ടു പ്രൂവ് ദാറ്റ് യൂണിയൻ ആൽഫ എ ആൽഫ എവിടെ ഉണ്ടെന്ന് കാണിക്കണം, tau ls-ൽ ഉണ്ടെന്ന് പ്രൂവ് ചെയ്യണം. ഫോർ ദാറ്റ് ഐ ടേക്ക് ആൻ എലമെൻറ്റ് ലെറ്റ് എ ബിലോങ്സ് ടു യൂണിയൻ ആൽഫ എ ആൽഫ. ദിസ് യൂണിയൻ ആൽഫ എ ആൽഫ എവിടെയുണ്ട്, tau ls-ൽ ഉണ്ട് എന്നാണ് പ്രൂവ് ചെയ്യേണ്ടത്. ഓക്കെ okay, this is our claim. Union alpha A alpha belongs to tau ls. This is our claim now. Okay, for that I take an element from union alpha A alpha. Okay, let A belongs to union alpha A alpha, which implies A belongs to A alpha for some A alpha naught for some alpha naught. Since this A alpha naught is a member in tau ls, since A alpha naught is a member in tau ls, as per the property of tau ls, there exists some R naught greater than 0 such that interval of the form A closed open A plus R naught will be contained in A alpha naught itself. And where is this A alpha naught? A alpha naught is actually contained in union alpha A alpha because it is a member in this union, which implies interval of the form A comma A plus R naught is contained in union alpha A alpha. Therefore, when you take an element in this union, we get this kind of interval is contained in that union itself. So, which implies union alpha A alpha belongs to tau ls. Now, to prove the intersection, you take an element from this intersection. Let A belongs to some intersection AI, I equal to 1 to n, where each AI എവിടെ നിന്നാണ് എടുക്കുന്നത്, each AI belongs to tau ls. Okay, which implies A belongs to AI for every I equal to 1, 2, 3, etc. n by the property of intersection. അല്ലേ, when A belongs to intersection, A will belongs to every set in that intersection. Okay, now where each AI is a member in tau ls, so corresponding to every AI there will exist some Ri, which implies there exists some Ri greater than 0 such that interval of the form close to A comma A plus Ri will be correspondingly contained in the AI. Okay, this is true for every I equal to 1, 2, 3, etc. And as this is actually same as the proof of usual topology. Now we want a radius R such that close to A comma A plus are contained in this intersection. You know that intersection is the smallest set contained in every set, correct? So we want a smallest R. For that we choose R equal to minimum of R1, R2, etc. Rn. Then R will be greater than 0 and R is the smallest among all of these. Okay, then what you can say, close to A, interval of the form close to A plus R will be contained in close to A plus Ri for every I equal to 1, 2, 3, etc. n. Correct? Because R is the smallest among all these Ri, correct? Noku, suppose this is a real n, A is a number here, and we have close to A comma some R1, close to A comma some R2, close to A comma some R3, etc. close to A comma some Ri. Then you take the R as the smallest among all these Ri, then R will be here something. Okay, then this interval close to A R will be contained in every interval, correct? So therefore close to A comma R is actually contained in what you can say, A comma A plus Ri for every I equal to 1, 2, 3, etc. n. So which implies the interval A comma R is contained in intersection because it belongs to every I equal to 1 to n close to A comma A plus Ri. And where this kind of interval is contained in, this is contained in AI, corresponding AI. So which implies intersection AI equal to 1 to n AI. So what can you say about when you take an element, sorry, this is not R, A plus R, A plus R. So what you can say that A comma A plus R will be contained in intersection I equal to 1 to n AI, which implies intersection I equal to 1 to n AI is a member in tau ls. So tau ls satisfies all the properties of a topology. Therefore tau ls is a topology on R. In a similar way, we can prove that tau RS is also a topology. So these are two semi-open interval topologies on real line.